Okay, so let's go over my discrete math collection. Um, my correction for that. So I'm not sure how many questions I'm gonna do today, but let's see how much time I have. So question one, we have for sets A and B, their symmetric difference A, the symbol B is a set of this. Use double inclusion to show that B is equal to A. Okay, so anytime we have show that use double inclusion, it means that I just show both sides. So then one thing is equal to this, on the other side it's also equal to this, so then it would be an equality from both sides. So that's kind of what the approach is. So what I did here was that I want to show this, and I wrote down the definition of this. So then in the part one, um, I assume that X is part of this, so that I'm from the left-hand side. Um, so basically, I'm assuming that okay, so here, what I'm doing is that I know that I'm gonna assume that I know the left-hand side of this thing is true. So then what that means is that my X would be part of this by the definition of A of this. My X would be part of this thing, and then part of A and B. And X would not be part of B by the definition of this, right? So since my X is part of this, then I know that mm, X is part of this and this or this. So then, because I know X is not in B and X is not in B or A, so X must be part of A, not like the symbol not B. So then I know that X has to be in A and not in B. So then I satisfy that X is in A, if you get what this means. And now what I do in the case two is that I assume that X was in B. So then X is not in A and B. So it's to satisfy the condition, X is in A and X is in B, so X is in A. So no matter what, for X in A, this thing has to be in A. Mm. I don't think I wrote this out very clearly, but this one is also the same idea. X is in B, so then X is in A and B because you're just using a smaller one, right? So that X is not in this thing. So X is in this thing. And then in the other case where X is not in B, then we have this case. So X of this, so A is also in this. As we show that both um this and this, both sides of this, is a subset of the other. So since the subset relations hold, then this holds, then the equality holds. I think the major idea behind this to make it slightly easier is the case that we see over here. Because we can break this down into A, B, and B not A. So then that's what this is actually saying is that we have, let's say, two sets. We can call this A and B. The left-hand side, let's call this A. The right-hand side, let's call this B. So what this means is that A not B is whatever's in uh, this area. So this is this. It's not, and then whatever B and not in A would be this area over here, like these elements in this area. So there's nothing in common with that. And that's a union of this, which is just both of this. So what I and ultimately end up doing is this I assume that X is part, like inside the first case, when I assume it's this thing over here. When I assume it's, let me first erase this so that's less colorful. So first when I It's too colorful here. So the idea behind this is that I need to erase this. I feel like it's way too many colors. So you don't even know what I'm talking about. So the idea behind this is that I broke down this thing over here into two cases. When it's this case and when it's this case. So in the first case, when it's A, not like everything in A, but not in B. So then um, it would just be the first thing over here and not in B. And then the second case is in B, but not in this. So then I work based on whatever I know, then I know I work it from there. And in the second case, when I assume it's part of A, then I would first break it down to cases when it's in B or it's not in B. And I would see that both cases satisfy the requirement. So the idea is that I break it down into cases of like, what is this, and I just use this first condition over here, this condition, to break it down into the first part and the second part so that I can just work it out from there. That's the idea of A, and I think it's pretty clear. For part B, it's just a classic kind of recursion question. Let Tn be the tuples in Z0, 1, 2, and with no consecutive zeros or ones, tuples of this, where no index I such that this thing is equal to 0 or this thing is equal to 1, set T of n equals to the size of T of n. Let A be the number of tuples ending with 0, B with 1, and Cn with 2. Show that An equals to Bn using a suitable bijection, and conclude that Tn is equal to A2An plus C. Okay, so for part B, what I do is I know that Tn has to pick either from 0, 1, or 2 and construct that sequence, right? And then there can be no consecutive zeros or ones. That's what the condition was telling about. So An is and then 1s, 0, 1, 2. So how I establish my bijection is that I know that x for any kind of sequence I have for A would be x1 to xn minus 1, and then the ending would be 0. So I sort of just define f of x to be y1 to yn minus 1 and then 1. So then such that like whatever my yi is, if xi is equal to 0, then I just do 1. So I just swap the 0 and 1 in this place. And I swap the 1 with the 0. And then 2 remains 2. So then this is basically my function. And that means that 0 and 1 is interchangeable because if it satisfies the requirement for 0, no overlapping zeros, then it should also satisfy for 1 because both sequences have to be valid for that. So then I can just swap it and it would still work out because there's no zeros and ones are still not consecutive. So then that means that this is a valid function and it's a bijection because 0 and 1 correspond to each other. So then based on this, my an is equal to bn. So I have proven that it's the case. And since it's equal, then I know that Tn has to be either ending in 0, 1, 2, because it's a partition, right? You can only have the 3 ending digits. So then since An is equal to Bn, then I could just do 2An is plus Cn, right? Pretty straightforward. Part 2, write a system of recurrences for An, Cn, and deduce that Tn is equal to 2 Tn minus 1, Tn minus 2. Okay, so this is what I want to show. I start off with what I know from the earlier part. Tn is equal to this. I know that An, because um, it cannot be consecutive, what is it called? If An ends in 0, then the last digit cannot be, then the previous digit before that 0 cannot be 0. So then I have this case where I have something over here, a valid sequence over here. And in order to be valid over here, I can only have 1 or 2. So this is just a sequence of Bn plus Cn, right? Bn minus 1, Cn minus 1. So then I know that Bn minus 1 is equivalent to An minus 1. So then I know that An is equal to An minus 1 plus Cn minus 1. And I can do the same for Cn. Cn is basically just Tn because it doesn't matter Tn minus 1 because you just have, there's no restriction on when it ends with 2 because you can have 0, 1, or 2. So then that's why we have Cn is just Tn minus 1. And then for Tn, it would be from earlier, just this thing, right? So then, and then this is An, this is Bn, this is Cn. That's pretty straightforward. um, then I would have Tn is equal to this thing. I just expanded it out, replaced Cn with Tn minus 1, expanded this thing out, 2 in each one. I just group the 2n minus 1 plus cn minus 1, and I have tn minus 1, tn minus 2. Then I just group it because I know that from earlier this part, I know that it's equal to tn minus 1. So then I would just have 2tn minus 1 plus tn minus 2, and I get what I need. So basically, this is just algebra, knowing the recurrences of each one, and just arguing, for instance, I have 0 here, then the previous one has to be 1 and 2. It can't be 0. So then that would just be Bn and Cn plus together. That's kind of the idea behind this. For part 3, solve the recurrence for Tn. So since I already have Tn in terms of itself, I just move the term so that it's equal to 0 on one hand. So then I move all the Tn terms to one side. I just replace my Tn with x's. So now I know that this is x squared, this is 2x, this is minus 1 equal to 0. This is my characteristic equation. I just solve for x and I get, this is just a classic quadratic formula. I get this, x is equal to this. So then my two roots are 1 plus square root 2 and 1 minus square root 2. And I both do it to the nth power. And I have coefficients a and b on the side. And I know that based on what I know that n equal to 0, t0 equals 1, t1 is equal to 3, t2 is equal to 7. This is just basically listing it out. I kind of know these already by hand. So then I just substitute in these equations in the boundary case of these cases. So then for n equals 0, a plus b has to be equal to 1. So I can say that b is equal to 1 minus a, right? And I can just substitute that into n equals 1, and I can put b in terms of a. So now I would get this. And I just do some algebra over here, and I arrive that my a is equal to this thing. My b, when I put it back, is equal to that thing. Okay, awesome. I just put this back. This is my a, this is my b. Okay, and then I have my original roots to the nth power. So then I just simplify it slightly, and I would get this. I just basically put the 1 plus square root 2 into this, and then I increment into n plus 1. And the same with the right hand, this side as well. So that's my recurrence formula. For part C, let a1, a2, a30 be positive integers satisfying this thing over here. Using the pigeonhole principle, show the following. Fix an integer k with 1 to 9. Show that there exist two integers among a1 to a30 for which differ by k. Okay, so this is just basically establishing the hose and making sure that it works. This is kind of like one of the slide questions that we did. So we have A1 to A30 positive, and these are different numbers, distinct numbers, so there's no overlap. So that's why we have our hose so that it doesn't repeat. So K is from this, so that there exists this. So what I do is I basically establish another set where I have all the numbers from inside the thing plus k. So then the maximum thing inside my thing is actually the maximum in this element is 50 plus k because I know the maximum is 50 and then I plus something more than k because I incremented each one by k. So then my maximum would be 50 plus k. So the set of my A union B would be A1 to A30, which comes from the A. And the B would be A1 plus K all the way to A30 plus K. So every element plus K, right? So then I know that the A union B, the maximum size of this would be 50 plus K. But at the same time, I know that through inclusion-exclusion principle, the A union B is A plus B minus A and B, right? So then I know that there's 30 elements in A and 30 elements in B. That's the way it's designed. And then A union B would be 50 minus K, right? Because like that's the maximum number that I could have because this I know that it's from 1 to 50 plus k. So that's the range. I'm capped at 50 plus k because my maximum is in B and B is definitely bigger than A because like my maximum element is 50 plus k. So that's why my A union B has to be maximum of this size. But at the same time, this leads me to 10 minus k when I simplify this expression. But since my k is only from 1 to 9, this means that my A and B must be positive. So by pigeonhole principle, since the none of the elements are strictly increasing, so there's no repeats, they're distinct. We must have AI equals AJ plus K. So the difference is K. So then that's where we get the pigeonhole, right? And then let's do part two, our last part of this question. For k is equal to 10, show that one fails. There might be two integers among this, which differ by k. So we showed here that there was 10 minus k, so that would be 0, so then there would be no repeat. So how do we exactly set up this counterexample? We can do it simply by just a greedy approach. Let's say that we have numbers from 1 to 10, right? There's no repeats of 10 here. This is the maximum interval of 10. So then I miss out 11 on purpose. And then 11 to 20 would not be possible. So then my next smallest one is 21, and I just do 10 more elements of that. And then I can do that again at 41 to 50. So that I'm within the boundaries and I already have 30. And there's nothing inside this example that allows me to have overlaps. So this example fails and it's a successful counterexample. So that's for question one. Let's end off here.